Hello and welcome back to our lectures. I hope everybody has managed to stay positive, except possibly for a COVID test, which better should be negative. Now, you might have seen that I have posted solutions for the first example sheet. So please take your time to compare your own work against my solutions. They are quite detailed and should be clear. But if there's any remaining issues, please let me know. I've also already posted a second example sheet. The questions should all make sense by the end of today's lecture. This second example sheet is quite substantial. I will probably post the solutions for it earliest in 2 weeks to give you sufficient time to go over these problems. But they're all core techniques relevant for this course. So please give all these problems your attention. The problems refer to the part of the course which we are currently in, the part on conformal field theory and the worldsheet perspective on string theory. We started with this in earnest last time. Let me rewind a little bit so that we remember where we were. In particular, I would like to go back to the first thing that we discussed. Well, this is a quick reminder of what we did to get into this conformal field theory setup. Firstly, we made a Wick rotation of the worldsheet time, making it purely imaginary, or in other words, putting a Euclidean metric on the worldsheet cylinder. And then we made a conformal mapping to the complex plane, where now time ordering has become radial ordering. And we can think about string propagating without interaction as originating at the origin in the complex plane and propagating out towards infinity. What I would like to expand a little bit on, so last time I was relatively brief on the relation between finite and infinitesimal transformations. In the little computation I'm sketching here, I'm discussing this for the worldsheet metric as an example of a tensor. And while we are doing it specifically for conformal transformations, the remarks made here apply completely generally. As the worldsheet metric is a rank 2 symmetric cotensor, and it is, as a tensor, invariant under coordinate transformation. This is a top boxed equation. And often we talk about this in terms of infinitesimal transformation, where we write the new coordinate as the old coordinate plus a difference, which is taken to be infinitesimal. And this is the so-called, we can regard this as a vector field, and this is the so-called generating vector field of the transformation. And by substituting in this into the invariance property, you can read off what the infinitesimal variation of a tensor, in this case the worldsheet metric, is. The infinitesimal variation is the transformed and the original tensor evaluated at the same point, taking the difference and neglecting any terms which are higher order in epsilon, so in our case higher order in psi. And so you can work out concretely what this is for a particular type of transformation. And I mentioned that this also relates to the definition of the so-called Lie derivative. So the way I've defined it here, this would be minus the Lie derivative of the worldsheet metric with respect to the generating vector field. And the minus sign is due to me taking here the passive interpretation of this transformation. Just to expand a little bit on this, so passive interpretation or interpretation as a reparametrization means the following. Up here in blue, we have a little piece of our worldsheet. There's a point P, and we can parameterize this with different coordinate systems, say the coordinate system sigma and the coordinate system sigma tilde. These coordinate transformations are related by a one-to-one map, which we also assume to be infinitely many times differentiable. And this is the passive interpretation of a transformation. It's the same point, but viewed in two different coordinate systems. And we ask how tensor components are related between the two coordinate systems. Another point, which is often taken in the mathematical literature, is the active point of view. So we take a point P and use the transformation generated by a vector field to move it to a nearby point P tilde, and describes this then again using coordinates, where of course moving from a point to a different point also moves from one coordinate value to a different coordinate value. Lie derivatives are usually defined in this context, and the difference between these two interpretations is just a minus sign. And that's so if you look it up in the mathematics books where it's related to an active transformation, it will be appearing with a plus sign. Good. Now let's go back to the slides. And I think we want to go also still rewinding a little bit where we were. Let's go to page 14, where we introduced a core concept, namely that in conformal field theory, we work with operator products as the primary objects, and then we take products between two operators and expand it in a series of other operators, which is then called an operator product expansion. And we discussed how one can, if need be, how this can be reconverted into commutators. Okay, I think I don't want to review the details, but this operator product always has a singular part, and this is a part interesting for the correlation function if we sandwich this operator product between two ground states. And then it also has a non-singular part. Non-singular refers to the limit where Z and W coincide. And this is the normal ordered product. This is one way of defining normal ordering of operators in a quantum field theory. And in the example at hand, it coincides with the more conventional definition of putting all annihilation operators to the right of all creation operators. Now, the operators that we consider are formal series in variables z and 1 over z with some operators as coefficients. At that level, there's no meaningful way to talk about convergence. It's a more formal object. But once we sandwich operators or products of operators between states in a Hilbert state, we get correlation functions, and then the concept of, or the question whether these infinite sums that we have are convergent or not play a role. We saw an example, and this represents the general case, that these operator products converge, or as one says, converge on the vacuum, if they are radially ordered. And that required us to have some thought about how we would then define commutators. Because in a commutator, we take operator products in two different orders, but we always can only make sense of them if they are radially ordered. So 37, as it stands, was not so well defined, but we found that we could encode the information that we want to know a commutator by making a choice of integration contour. That's one of the most important formulas that we have, this encoding of commutators using choice of contour. And well, then we convinced ourselves that we can get back commutators, and then we started to talk a bit about the energy momentum tensor. So classically, this is the product dx with itself. In the quantum version, we now, of course, have the problem that the operator product expansion of dx with itself contains a singular term. So to have a well-defined operator, we define in the quantum theory T of z as the normal ordered product. And that means we take the product, we subtract the singular terms, and then the limit is finite. And the singular part of the operator product, which is denoted with this contraction symbol here, is the contraction which you might have encountered in quantum field theory also in other formalisms. Here we define it this way. Now, using 34, which is the OPE of dx with itself, one wants now to compute what the OPE with the energy momentum tensor is, both the OPE of the energy momentum tensor with the field dx and also the OPE of t with itself. And this can be done with only the OPE 34 as input if one knows about Wick's theorem. More precisely, Wick's theorem has various versions, at least 3 of them I'm aware of, and this is the version of Wick's theorem which concerns products of normal ordered products. Wick's theorem is essentially a combinatorial device which helps one to do the combinatorics right. And what one has to do is the following. So the situation for us is that we have a product of 2 normal ordered products. And we want to express this again as a series of normal order, just one normal ordered product. But this will in general be an expansion. And the theorem tells us what we have to do is we should sum over all possible contractions where between the operators in one set with the operators in the other set. This is most easily understood in an explicit example, and I take the example which is relevant for computing the TT operator product expansion. Namely, we have a normal ordered product AB and multiply it with a normal ordered product CD. So what does Wick's theorem say? It says sum over all possible contractions between operators in the 2 sets. So in this situation, what we can do is we can do double contractions, but since I only have to go from one set to the other, there's exactly 2 possibilities. Then we can do single contractions. There is 4 of these, and then no contraction, and this is a purely normal ordered object. And what we normally want, what we will want to know for the TT OPE to get these terms here is we have to use the first 2 lines. Okay, good. And yeah, maybe I want to say something about the structure of the OPEs already. If you look at 45, 46, you see some structure. So if we multiply energy momentum tensor on dx, then we see that the leading term reproduces dx. So dx is a kind of eigenoperator of t. It gets reproduced if I multiply it with t, comes with a second order pole, and then there's a first order pole where the derivative is 1. The OPE of t with itself has a similar structure. In particular, if you look at the terms which we also have in 45, we have a second order pole and a first order pole. And these look similar, except that for t here, we have a different coefficient. Here we have a 2, and here we have a 1. And that will have to do what we will later learn is the so-called conformal weight of these operators, where t will turn out to have weight 2, whereas dx has weight 1. The energy momentum tensor has also another specialty that has a further higher order, 4th order pole, and that is something that we will try to understand in more detail later on. So if we now have, let's assume that we have done the computation during the Wick theorem and we have obtained the TT OPE, we can get some commutators out of it in the following way. We write T of Z as a formal Laurent series. And then using the residue theorem, which explained last time, we can project out the Laurent modes. And these are familiar looking objects, and we sum infinite sums quadratic in the coefficients alpha of dx. So these are the operators that we have already encountered previously. And with our OPEs 45, 46, we can compute commutation operators between L's and alphas, which is given by 50. That's again example where we can see that somehow the LMs acts on the alphas, because we take a commutator L with alpha and another alpha is split out. So somehow a Tx on dx, and therefore the L's x on the alphas. And there's a bit of reshuffling, but is consistent with the integer indices that we have. Here we have m and n. So on the left-hand side, we have m plus n, and also on the right-hand side. So this is another one of these so-called Z-graded Lie algebra structures that we have, where commutators are considered consistent with an integer labeling of our generators. Now, what about if we take 46 and compute the LM-LN commutator? Well, the first term that we get up to here just gives us a Witt algebra. So this would be the Lie algebra of infinitesimal conformal transformations. And if this was all, we would say, okay, that's very clear. The operators LM represent conformal transformations on physical states. But there's something going on because we get an extra term. This extra term is proportional to the unit operator. So it does not introduce any new object which does not commute with the else. Therefore, this is called a central extension of the algebra because it brings in on the right-hand side an object which is proportional to the unit operator and therefore commutes with everything. It's consistent with the grading. It only appears if m plus n add up to 0. That's consistent with the grading. And the term is absent if we restrict to m equals to 0, m equals to -1, m equals to +1, which is the SL2C subalgebra, which, as we discussed before, is the subalgebra which can be exponentiated to give us finite conformal transformations on the Riemann sphere. So mathematically, this is called a central extension. In the physics context, this is called an anomaly, in this case, the conformal anomaly. Sorry for misspelling here. Anomaly is generally the terminology of a symmetry, which we have in a classical theory gets modified in the quantum theory. That might be a good thing or a bad thing. In the present case, it's a good thing and an interesting feature because it does not introduce any inconsistencies into the theory. It just makes the quantum theory much richer and interesting than we expected from the classical consideration. Okay, this is some remark that I already made before, that from the coefficients in this OPE, which are 1 and 2 respectively, we can read off that dx is what we will later learn is a primary conformal field of weight 1, and T will not be quite a primary conformal field, but something more general, which we call a quasi-primary with a weight 2. But this is something that we come back. Currently, what I would like to focus, if you want to do some work, is to work out these OPEs and to see that you can reconvert them into commutators. And we will come to the deeper meaning a bit further along these lectures. Okay, that was this remark. Now, let me come back to one question that you might have, excuse me, have asked. I focused on the correlation function of the derivative of the scalar field with itself. Normally, in a quantum field theory, we would look at the correlator of the field with itself. So what is wrong with x? Well, you can see what is wrong with x if you look at the result for the two-point function of x, because the singular part involves the logarithm, and the logarithm is not a meromorphic function. That is, it is not holomorphic up to poles, but it is a function which is multi-valued in the complex plane. It is branch cuts. And the conformal field theory formalism, the whole framework requires that we have single-valued functions with at most poles. So mathematically, that doesn't fit into our framework. You can also say in a more physicsy way that something is not quite right with this correlator from our expectation that we have conformal invariance. Namely, consider what happens if you make a dilatation, a rescaling of z by a real factor. The scalar field x naively has weight 0, so it should be invariant under such rescalings. But if you make the rescaling on the right-hand side, because of the properties of the logarithms, you will see that the right-hand side transforms with a shift. So you can't even associate a specific weight with x on the right-hand side, because it does not the right-hand side does not transform with a power of lambda, but with a shift in lambda. So in conclusion, x of z does not transform tensorial under dilatations, and therefore under part of the conformal transformations. It is not a conformal field or conformal primary as we will define it later. But no worry, we still have a perfectly valid conformal field theory, which we can describe in terms of operators. It's just that the operators, which are really the physical operators, are dx, any higher derivatives of x, and we will discuss these in a few minutes, normal ordered exponentials, and then products of these. We will see that such operators create all the states that we need. In particular, if we turn to the string theory interpretation, with these operators, we will be able to create all states that we know that a quantized string has. And that also explains why they're called vertex operators, because we can use these operators to create or annihilate states at any given point on our worksheet. Okay, good. So carrying on, we would now like to work out properties of these exponentials so that my claims can be substantiated. For this, in fact, the XX OPE, despite its branch cuts, is quite useful as a device, because it's a kind of master formula from which I can derive other OPEs, which then are single valued. I give you here the results because I would like you to practice working out these OPEs yourself using the XX OPE and Wick's theorem. So let us discuss what the results tell us. 55 is dx acting on an exponential, and this reproduces the exponential with some eigenvalue. So the exponentials are, in a sense, eigenoperators of dx. The interpretation that we will learn later is that dx is something like a current, and e to the ikx like a state carrying a charge. So what this OPE does, it reads out the charge that this state corresponding to the exponential carries. So this is this OPE here. Now you might ask, how do I work given that I know the XX correlator? The exponential of an operator is defined through the Taylor series. So what you have to do is you write out the exponential as a Taylor series, taking into account the normal ordering, and then you apply Wick's theorem and repackage the results to see that you reproduce, again, an exponential with some overall factors that you pull out. The same technique applies to 56. It's a bit more complicated because inside the energy momentum tensor, we have twice dx. So there is double and single contractions, and you need to do a bit more combinatorics. But like dx, it turns out that e to the ikx has a second order pole and then a first order pole with a derivative on acting on here. And then there's a particular, if you like, eigenvalue read out of here, which, as we will learn later, tells us what the so-called conformal weight of this operator is, which will turn out to be k squared over 8. And then remains the question, what happens if we multiply exponentials with itself? And on exponential, it essentially closes. On the right-hand side, I've written it first as a bilocal operator, which depends both on z and w. But ultimately, we want to have local operators only depending on one variable. And the convention is always, if I have an operator depending on z and operator depending on w, then everything is to be expressed in terms of the operator depending on w with coefficient functions which are powers of z minus w. And so you have to, from here to here, you have to expand and then to keep all the singular terms. And in the cases we are interested in, only one term will be, one or two terms will be non-singular. Will be singular, and most terms are non-singular and not so interesting for us. Now, that's doing it with two exponentials is a bit challenging if you write out two infinite sums and then you have to do all the various contractions, which of course can be infinitely many. That's a bit hard to work out. Of course, in principle, you should write everything out until you see a certain pattern and then try to prove the result by complete induction. But to make your life a bit easier, I give you in 59 a formula, which is of the Baker-Campbell-Hausdorff or BCH type, which says if the contraction or singular part of an OPE is proportional to the unit operator, then the product of two normal ordered exponentials e to the a, e to the b is a normal ordered exponential e to the a plus b with a coefficient which is the exponential of the contraction. So this formula is given for you as a shortcut to make your life a bit easier. Just to remind you or tell you about Baker-Campbell-Hausdorff formulas. So if we just have scalar quantities a and b, then the functional equation of the exponential function tells us that e to the a times e to the b is e to the a plus b. You can ask how this is modified if a and b are non-commuting quantities, and this is what is answered by these Baker-Campbell-Hausdorff type formulas. And turns out that the first correction term, the leading correction term, if you do it in the language of commutators, is e to the 1/2 commutator a, b. And then you have further terms. The simplification, which normally is sufficient to do this in quantum mechanics, is if a and b commutator is proportional to the identity, then there are no higher corrections. The reason is that the further terms are again exponentials, but is commutator AB commutated again with A or B. But if AB commutator is the identity and hence commutes with everything, then all the higher terms are zero. And commutators in quantum mechanics, like position X commutated with momentum P, is proportional to the unit operator. So for this kind of operators, you can work with the leading part of the BCH formula. Now, there's a whole industry how you derive such relations to higher orders, but for us, this is just a tool which is stated and which we use as given. Moving on. Again, a central concept in conformal field theory, and very important also for us interpreting conformal field series as string series, is what is called the operator state correspondence. So the idea is, if we insert an operator P at some point on our surface or worldsheet sigma, then this generates a state. Well, if we just insert one single operator, then of course we can always choose our coordinate system such that the insertion point is the origin of the complex plane, and maybe we use this in order to understand this correspondence a bit better. So as an example, I can define a state cat k by taking the normal ordered exponential, apply it to the ground state, and evaluate this at the point origin of the complex plane, which I have written here as a limit. What I claim is that the resulting state is an eigenstate for the operator P, which in string theory is a momentum operator, or more precisely the component of the momentum operator along the direction which we are currently looking at. Remember that we have kind of truncated string theory to one single space-like direction. P would be the momentum along this direction. Anyways, insertion of an exponential at a point, I claim, creates a momentum eigenstate. Now, how can we verify this? Let's see. Well, there's two ways, and I recommend looking at both. One is we can write the operator P as a contour integral, projecting it out of the X, and then use a known OPE to verify that this statement holds. That would be along the line how we have done this before. But there's a second way of doing it, and I will now go over it because it's quite instructive to understand the state operator correspondence. So alternatively, it goes as such. We remember that the ground state is defined as being annihilated by the alphas with positive mode number m and by the operator p, the momentum operator. And with this knowledge, we can write the normal ordered exponential explicitly using its alternative definition as saying put all annihilation operators to the right of all creation operators. That means that all the alphas with positive n must be to the right of all alphas with a negative n. By the way, here's a typo which I missing 1 over n, which I detected, which I've filled in. So please correct this on your slides. So this takes care of the normal ordering of the alphas. Then x and p, again, p annihilates the ground state, so we put it to the right of x, which x non-trivial. Now, what happens if I take this here and apply it to the ground state? Let's go term by term. So first, what about this term here, where we have alphas with positive n? Well, these annihilate the ground state, so I get e to the 0, which is 1. So this does not act on the ground state. The same with this term here. P annihilates the ground state, so we get modulus of z to the 0, which is again 1. So no action. Then e to the ikx acts non-trivially. So this will do something with the ground state. The alpha n's with n negative also act non-trivially on the ground state, but taking into account that here n is negative, they come with positive powers of z and z bar. So in the limit, z goes to infinity as a term with the alpha n's, which on other points of the worldsheet would have a non-trivial effect, again acts trivially. So the only thing which contributes is e to the ikx. Now with regard to our exercise to verify that this is an eigenstate of p, we can now use the commutation relation of x times p and verify this relation here. To do this, you Taylor expands the exponential and compute the commutator of p with the exponential of ekx. If you do this for a few terms, you see how by induction the commutator works out, and then it's not hard to see this indeed a momentum eigenstate. Similarly, you can show if I insert the derivative of x at the origin, this gives me something proportional to alpha minus 1 applied to the ground state, and higher derivatives give you all the alpha minus m's applied to the ground state. But momentum eigenstates with an arbitrary chain of alpha minus m's applied are the basis of our Fock space, as we know from our sketch of quantization from part 2. That means that the fields, or as we call them in string theory, then the vertex operator, derivatives of x and normal ordered exponentials are precisely the operators which we need to create all the possible states. What we have gained is that now with these vertex operators, we can create the states at arbitrary points in the worldsheet. In this formalism, we then can think about states at the origin as, say, an incoming state in a process like cat v, and correspondingly states at z equals to infinity as an outgoing state, bra v. This is to be taken with a grain of salt with respect to the space-time interpretation, because from the space-time point of view, particular coordinate values on the worldsheet do not have an invariant role. But for sake of concreteness, you can, if you like, imagine a string being created at worldsheet position z equals to 0 and propagating along and then ending up as a state in infinite future as state bra v. Okay, and then since we now can insert or create and annihilate states at any point in the worldsheet, we can look at correlators where we have an in and an outgoing state, and then some further states interacting with this in between. And this is what I've indicated here. This would be a worldsheet correlation function. And these worldsheet correlation functions are the building blocks for scattering amplitudes between the corresponding string states, with one additional tweak. In a conformal field theory, I can talk meaningfully about correlations between vertex operators at different points in the worldsheet, but as already stressed, from a space-time stringy point of view, positions of operators on the worldsheet have no invariant meaning, but then the string scattering amplitudes are technically defined not as the worldsheet correlation functions, but as the integrated correlation worldsheet functions where integrate the vertex operators over all possible positions. There's some fine print to it, but before explaining the fine print, let me kind of graphically illustrate what I've just talked before. So let's start with a situation where we insert a single operator in the complex plane. We can then take this to be the origin, and then I've drawn a disk around this point, and this would correspond to a string being created and propagating for a while. And intuitive way of thinking about this is a semi-infinite cylinder with the point at the origin mapped out to infinity, representing a state which is asymptotic, which is either traveling in or traveling out of a process. Whereas then the other end here represents where we end the time evolution. And then the state corresponding to the vertex operator is the vertex operator inserted at the origin. We can take two vertex operator insertions in the complex plane, one at the origin, one at infinity. This then gives us an infinite cylinder, and we can think of this as an amplitude where we create a state in the infinite past, let it propagate to the infinite future, and then ask what is the probability to find the state V1. And this is this correlation function here. And we can go further. We can introduce more operators, let's say 4 of them. And if I keep one point at infinity and the other at the origin, this is an infinite cylinder, which again describes the propagation of one string state, of one string for an infinite amount of time. But now the string interacts in between with states which are represented by operator insertions at Z3 and Z4. And the analytic expression would be something like this. Now, to make this look more democratic, I have in this line here reformulated or rescaled this as a finite cylinder where all 4 states correspond to cut out holes, which you can think as the 4 states entering into a interaction process. And to make it completely democratic, I've here deformed it in such a way that it looks like a scattering process between 2 incoming and 2 outgoing string states. So that would be the space-time interpretation of such a process. To answer the question, how can I tell what is in a process an ingoing and what is an outgoing state? This is specified by the momentum k. Now, all these vertex operators will contain a normal ordered exponential e to the I k1, k2, k3, k4 times x. And depending on how I choose these momenta, I can evaluate such an amplitude for certain states being ingoing states, initial states, and others being final states. Generally, such scattering amplitudes are analytic in momenta, or actually in complex momenta. So one can analytically continue between situations where a certain state is an incoming state, and you could also take the same particle to be an outgoing state by making an appropriate analytic continuation of the momenta. So that is the true space-time meaning of the process is not encoded in the worldsheet coordinates, but in the momenta that we put into our vertex operators. And here's finally another way of representing this amplitude, kind of going back to the complex plane, but now making it the Riemann sphere with 4 operators, again, democratically inserted. Now, let me come to the fine print that I mentioned. To have a space-time interpretation, we need to consider the integrated correlation function. So we need to integrate over the position of the vertex operators. However, if we are on the Riemann sphere, we know that there is a part of the conformal transformations which exponentiate really to a group, SL2C, which acts on the Riemann sphere and can be used to move around points. And this is a symmetry that we have to take into account to avoid overcounting equivalent configurations. The group SL2C acts in has 3 complex parameters, and one can show that this corresponds to the freedom with these SL2C transformations to map 3 points on a sphere to arbitrary given positions. For example, the standard configuration that one chooses in computation of scattering amplitudes is to put 1 point at the North Pole, or equivalently in the complex plane at infinity, another point at the point 1 in the complex plane, and another point at the origin of the complex plane. And then if you have more than 3 vertex operators, then the 4th and 5th operator and so on need to be integrated over. So to avoid the overcounting a string process with 4 external states would be a worldsheet correlator with 4 vertex operators, 3 of which fixed to standard positions, infinity, 1, and 0, and then only the 3rd vertex operator with a position z, which is integrated over all possible positions on the worldsheet. Okay, can now go back to my slides, I think. Sorry, here we are. And I think this is where we left off. And here I've recapitulated for you how this SL2C transformations work. This is a so-called Möbius group, which acts by fractional linear transformations on the Riemann sphere. And the standard fact from the theory of complex functions that one can then use these transformations to map any 3 points to any 3 given points, with this being a convenient standard choice. Okay, very good. I think that is the end of this part. Are there any immediate questions? And I think with the material in this part, you can attempt all the problems, I think. But we will now have a further part 4, where we go over the conformal field theory material again, but in a top-down perspective. So now I will make general definitions and statements, and we will see how what we have seen in this part here fits with these, it is motivated by these definitions. Okay, good. It's a few minutes, so I can give you already a little bit of introduction into this part. You can also already find the slides for this part on your learning environment Magic webpage. And what I first would like to do is, for educational purposes, tell you a bit more about conformal symmetry in general dimension before we then specialize to 2 dimensions. I think that is something which I can probably do just with the time that we have left before. So going back to the very beginning, a transformation is conformal if it changes the metric by a positive factor, which is allowed to depend on the point where you are in space or space-time. These transformations therefore do not preserve lengths, but they preserve angles. In other words, they preserve the shape of things, but not their size. Now, let us take in particular a background which is flat. Let's say Minkowski space. Infinitesimal conformal transformations are then generated by vector fields, and they must have the property that the matrix which we have fixed, in our case the Minkowski metric, is modified so that it goes back to itself multiplied by a function to lambda. One can work out what the general solution for the generating vector field is. And let me stress, this depends on the metric that we choose. If you choose a completely general metric, then there will be no conformal transformations at all. But if we choose a flat background, there will be the maximal number of such transformations. And that's the situation we now analyze. And you can show that the most general generating vector field looks like this. It has a constant piece, it has a piece linear in the coordinate, and a piece quadratic in the coordinate. The coefficients have some constraints. So the coefficient of the linear part, the linear term, has a completely antisymmetric part and a pure trace part, but there's no symmetric traceless part. So in other words, I think this is called shear. So there's no shear. Now, shear transformations are those which distort shape. Whereas antisymmetric part is either a rotation or Lorentz transformation, and the trace part is a dilatation or rescaling of the size. And then there are also terms which are quadratic in X, and this is a bit harder to figure out, but one can show that these can be parametrized in terms of a vector beam U. So the resulting parameters are then alphas, one scalar, two vectors, and one antisymmetric tensor. And what do they mean? Well, the parameter R mu parameterizes translations, and the corresponding generator is the momentum operator. Then this antisymmetric mu nu parameterizes, since we are in Minkowski signature Lorentz transformation, in Euclidean signature it would be rotations. So these are the Lorentz generators. Then we have the scalar alpha, this is dilatations d. And then what is this extra stuff which has to do with this quadratic terms in the generating vector field? Well, these are called the special conformal transformations. They are parameterized by a vector. And as you can see from this formula, these do not act linearly. More generally, they don't act by affine transformation, but in a more complicated way as fractional linear transform. No, not even fractional linear transformation, because we have quadratic terms. So it is a more complicated type of transformation behavior, which in particular can map points to infinity. So that makes the special conformal transformations special. If you just augment the Poincare group by dilatations, you have the so-called affine conformal group, which still acts by affine transformations, meaning linear transformations in translations. But with the special conformal transformations, if you really want to make sense of these transformations, you need to add a point or points at infinity. And this is called the conformal compactification. Conformal compactification of Minkowski space specifically adds in one particular point at spatial infinity, but the same point for all times. Now, if I take this full conformal group, including the special conformal transformations, then this group, as I think I've already mentioned, is SOD, which is related to the Lorentz group by adding +1 in each slot. And you can work out standard generators for this essentially. If you take linear combinations of translations and special conformal transformations, then they have the same Lie algebra as rotations or Lorentz boosts have, which allows you to show that it is this algebra here. Now, some general remarks about scale invariance and conformal invariance. So the first point is there is a Noether current for scale invariance, and it is obtained from the energy momentum tensor by contracting it with one coordinate. So if this current has a zero divergence, then you have scale invariance. Now, scale invariance does not imply by itself conformal invariance. We have seen this from the group structure. I can have a smaller group of affine conformal transformations, which closes among themselves without the special conformal transformation. So whether we have just dilatation invariance or full conformal invariance needs to be investigated case by case. criterion for conformal invariance is the tracelessness of the energy momentum tensor. But it is not so easy or so unambiguous to analyze, because the energy momentum tensor is not uniquely fixed. You can always change it by improvement terms, which consist of adding derivatives of a higher rank tensor. Just my alarm went off, so I will now wrap up, but maybe since I'm in the middle of this transparency of this sheet here, I will complete this before ending the lecture. So that is what makes it tricky. Now one knows examples of conformal field theories, and this amounts to analyzing often the situation given a theory with scale and Poincaré invariance. The question is, can I find improvement terms so that I can make the energy momentum tensor traceless? If one is in this setup, then indeed scale invariance and conformal invariance are the same, because once you have all these conditions satisfied, the trace of the energy momentum tensor is just the divergence of the dilatation current. So the conditions for having conformal invariance and the condition for having just scale invariance coincide with each other. But well, I'm not an expert in this field, but apparently the difficulties are in that one has to discuss the energy momentum tensor up to improvement terms. And finally, even if we have classical scale or classical conformal invariance, this can be broken by quantum effects. And the measurement device for this is the so-called trace anomaly, which is the expectation value of the trace of the energy momentum tensor. This can, even if classically the energy momentum tensor is traceless and the dilatation current is conserved, it can happen that in the quantum theory, there's an anomaly which makes this trace non-zero. And just as a concluding remark, the modification of the conformal Lie algebra with this central extension is precisely an example of such an anomaly. This can be analyzed using the trace anomaly, though we did not take this route, but rather just worked out the commutators and observed that we have modification. Okay, I think I should not run too much over time. So let me close the lecture. So far, there is no urgent request for question to be answered. I'll hang around until you all have logged out, but otherwise, wish you a good week. And please have a look both how you did on the first example sheet and try to start working on the second using what we have learned in the last two lectures. Okay, end of the lecture now. Looking forward to seeing you all in a week. Bye-bye.